Hello and welcome once again for another ES340 video. This is day 20, part B. I'm going to keep this part short and not get into necessarily all the gory details, but I think that I want to highlight some of the key parts of this because in general we would like to be able to analyze systems that have multiple components, right? So we already did in the last video. We discussed the partial pressures and things like this that are related to multiple mixtures, right? So we have multiple components in the system in that case because we have maybe multiple different gases and whatnot. So I just want to highlight the key details, and I'll leave it to you to go read it in more detail if you're interested and think maybe you might be taking things like heat transfer or whatnot in the future, where you might be interested in just working through details of partial derivatives and whatnot. But the first topic is the partial molal quantity properties. So the basic idea here is that I can write an extensive variable, an extensive variable that we're going to call x here, capital X, which is equal to x, and it's going to be, it's going to require two properties to define it, and then also the molar quantities if I'm in a mixture. So I'm assuming I'm in a mixture. You could collapse this down to just N1 for full generality. It could be N1 only if it's not a mixture. So this encompasses any type, really, this notation. So this X is going to represent some kind of extensive property that's a function of temperature, pressure, and whatever the molar quantities of each gas are, or each component of the mixture. It doesn't have to be a gas, right? So each component of the mixture are however many moles of H2O and however many moles of CO2 and so on, that will be contained here. Now, what kinds of extensive properties could X be? We said X is an extensive property, right? It's so it could be any manner of extensive properties, right? It could be capital V, which is the volume, or capital H, which is the enthalpy, not the specific. These are not specific quantities. These are the capital values, the capital letters. So, the enthalpy, not the specific enthalpy. The volume, not the specific volume, and so on. U, S, right? All of these could be are examples of what the extensive variable could be, and we're just kind of writing it this way so that it's in its full generality. Now we can write X, so remember this could be V, H, U, S, whatever, in terms of partial derivatives, dx, d, to be as general as possible, d alpha n1, where alpha is some scaling factor. So basically alpha will scale each of these molar quantities as needed, times n1 plus dx d alpha n2 times n2 plus dot 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 plus dx d alpha nj. Okay, so so the x can be then whatever that is, v h u s, can be expressed in this way when we're dealing with a mixture. So the partial mole quantity is defined as one of these, basically. And we're going to make it so that it's it's properly in mole form. Oops, dx. Excuse me. So this is going to be the partial mole quantity for a particular thing. So it could be the partial volume. It could be the partial mole volume, right? It could be the partial mole internal energy, and so on. All of those things will have these partial mole quantities, which are related to the partial derivative of that quantity with respect to the number of moles of that quantity, right? So if I had, for instance, a mixture of O2, which is oxygen, and N2, which is nitrogen, then the partial, say, volume with respect to oxygen would be related to the number of moles of oxygen, right? That's the idea here. Okay, so these quantities then, and we can express the full quantity after the mix. So this, after having this mixture, as follows. So basically, I can take this partial derivative for a particular quantity and the particular type of gas or whatever, and if I sum them all up, that's going to give me the total volume. So this, if x is v, right, or the total internal energy or whatnot of the system. So I can basically break it up into parts and sum up all of those parts to get the extensive quantity of interest. Okay, and if I want to actually evaluate these quantities, then I can do them in terms of limits. So we already said that xi is equal to dx dni, Tpni all held constant, and L. This is not Ni. So this is holding all of the other, did I write that wrong here too? This should have been L. So this is basically holding all of the other quantities, the other molar quantities, constant there, is equal to the limit, because any derivative is a limit anyways, as delta Ni goes to 0 of delta x over delta Ni, holding these other things constant. Okay, so in this case, just like any derivative, you can take the limit as you go here, as that shrinks, as the delta Ni shrinks towards 0. And obviously you can get more accurate if your delta Ni gets smaller, right? So if you're trying to get an accurate estimate of this derivative, you can shrink the distance between those points and you should get closer to the true derivative. Of course, we're making assumptions about how the continuity of the functions that are in play here, and things like this. But for normal systems, things that have enough molecules of gas in there and things like that that force the system to behave like our assumptions, the better, the more accurate these things become, right? So if I'm dealing with just like 1 full mole of air, as an example, mixed with 2 moles of nitrogen, well, there's a lot of atoms that are involved there, in terms of the total number of molecules that are interacting and whatnot. So this is going to behave quite well. The assumption that we have a continuous function there is going to be approximately true, basically, and so this is going to behave quite well there. If you get down to just a few atoms interacting, then things get a little hairier, if you will, and these assumptions go by the wayside. So you do have to kind of keep track of those kinds of assumptions. But for most macroscopic systems, these kinds of things are going to work well. So basically, if I want to find differences, so imagine I want to find the change in volume of a mixture. And I can look at each of the components. And I can just do something like this. This is the lowercase v, by the way. So this is a capital V, and this is a lowercase v bar. So and I can do this for this means that delta V mixing is equal to the sum, if I absorb all of those quantities in, of Ni times Vi bar minus V lowercase vi bar. And I can get similar things. Again, this can be any x, basically. Any extensive property can be written this way. Ni times hi bar minus lowercase hi bar, and so on. I could do that for, this is u, sorry, not h. Lowercase u and capital U bar, and so on. Okay, so you can, and you can replace h and s and write out the same formula. Okay, so etc. for any of those quantities. Okay, so now we can actually handle mixtures by doing this. This kind of leads nicely, essentially directly, into something called the chemical potential. So remember that we could write, we can always write everything out in terms of one of two types of functions, right? We had the Helmholtz function, which we've already seen a lot of, or the Gibbs function. So the Gibbs function G is one of the types of functions that can kind of give us the entirety of thermodynamics can be absorbed into the Gibbs function, at least everything that we've learned here. So the chemical potential kind of stems directly from the Gibbs function relating to mixtures like this, okay? And that chemical potential ends up being the derivative of the Gibbs function with respect to one of these components. Okay, so if we take the Gibbs function, we think of the Gibbs function as being one of these kinds of extensive properties, right, of the system, then you can see that we replace that here with the Gibbs function, taking the derivative there, and this is what's called the chemical potential. And the chemical potential actually becomes of great interest, particularly for chemists, or chemical engineers, things like that. So the chemical potential is actually an important property that in this case is an intensive property that describes things for chemicals particularly as they're heading to equilibrium are in equilibrium. Okay, so this becomes very important when we have mixtures, and just like above, we can write this out in terms of the molar quantities, right? Summing up all of the molar quantities. There's similar things that can be related in terms of for the Helmholtz function as well, and I encourage you to read about that in the book. But I'm not going to go much again into the details here, aside from just kind of pointing out that we have this chemical potential, and it relates to these mixtures in terms of the Gibbs function. Okay, so that's going to be kind of the key detail here. The final topic is the fugacity. And the fugacity relates to the chemical potential. So the chemical potential can actually be written out as mu equal to R bar T natural log of F plus some C, which is a function of T. This F here is the fugacity. Okay, so this is the fugacity, and when I have when I don't have a mixture, when I am just dealing with non-mixture components, I can actually say that the fugacity relates to the pressure in the following sense. When the pressure is low, the fugacity and the pressure coincide, so they become the fugacity itself becomes like the pressure when we're dealing with low pressure. So as we get closer and closer to a pressure of 0, the fugacity and the pressure can be thought of as the same thing, essentially. This is not true exactly when we have mixtures. The fugacity then, in that case, becomes a molar quantity. So basically, special case, pure phase, pure substance, not pure phase, which obviously those two things are different. In the case of a mixture, the following key detail is true. The limit as the pressure goes to 0 of F bar, the fugacity, over Yi times P. Remember, Yi here is the Ni divided by N. Right. So it's the mole fraction here. So if in that case, the fugacity, this goes to 1. The fugacity relates to the partial pressure, right? Yi is times P is like the partial pressure that I'm dealing with here. So it relates to partial pressures in mixtures. But again, this is again if as the pressure goes to 0, right? So as when the pressure is small, when it becomes more and more like an ideal gas, the fugacity and the pressure coincide, or the partial pressures coincide. And that's sort of the key details that I really wanted to cover for this chapter. I highly encourage you to read the rest and see some of the details, but these were the key things that I wanted to cover from this part of the chapter. That's all that I have for this episode. See you again next time.